Okay, so welcome back to another video. So here we have a definite integral from 0 to a of 1 divided by a plus b to the power x dx. So two different values for a and b, and with this being the case, we want to find a nice general closed form depending on our values for a and b. So for something simple like this, it relies heavily just on, u-substitution, but the first step really is the u-substitution, but you have to choose carefully on what substitution we're going to be using specifically. So after that, and I'll give you, the spoiler that substitution is going to have to rely on some trigonometric functions to do that replacement. And then it just follows from a bunch of simplifying and then a lot of applying natural law properties to simplify it down to the closed form that we will want to find for. So before we get started, I actually just like to ask you guys a question, and you can post on the comments down below. So what values of a and b such that are depending on those two values such that our integrand is actually still convergent value, but not divergent, so undefined in other words. So you just let me know in the comments down below what number satisfies the followings for a and b. So with that, why don't we actually just get started? So I'll first say that for capital I, that depends on the function for two values a and b. So we put that down. So let our u sub b, so we're actually not going to use a, the typical standard variable on its own, like u equals whatever. Instead, we'll let b to the power x, we'll let that be equal to the following trigonometric substitution. You can actually play around with other stuff as well, but this is actually tends to be the more easier, approach, or rather the substitution. So we'll let b to the power x equals a times tangent square theta. So with this in mind, so what we want to do is, of course, we want to solve for theta on its own, then when we plug in the values. So, and this will also help because we actually need to change the bounds afterwards when we're going to a different, variable. So if I do this all on its own, then that means I have that theta is just simply just going to be equal to the inverse tangent of the square root of b to the power a and then divided by a. Okay. And so now let's actually differentiate the first line over here. So that means with b to the power x in respect to the x. So that means that's just b to the power x, then times ln of b dx, and then set this equal to, so this applies some chain rule involved, and then take the derivative of the inside of that input. What we get is 2a, then multiplied by tangent theta, multiplied by secant squared theta, and then d theta. Okay. And so what we want to do is that, of course, when we actually do the substitution, we want that dx by itself, that now, replacing that will be a whole lot easier. So of course, I can actually just divide the b to the power x and then ln of b to both sides. And of course, we have that b to the power x is equal to this, so I can actually just substitute that value. What we have now is that dx is simply just going to equal to 2 times a tangent theta, then secant squared theta divided by, so ln of b multiplied by a and then tangent square theta and then d theta. And so this is great that now that we solve for theta, we can actually just plug in for our bounds a to 0 back into over here. So our top bound is going to be the inverse tangent of the square root of b to the power a divided by a, and then our lower bound is going to be the inverse tangent of the square root of, so I plug in 0, so that means that's going to be 1 divided by a. Close that off, and now we actually just put in the substitution, so replace the dx with everything over here. So let's see, I have 2a, then tangent theta, then multiplied by secant squared theta, all this being divided by ln of b, and then a times tangent square theta, all this being divided by, so I have a plus b. So the thing is that b to the power x, if I replace this, so that means I have a plus a times tangent squared theta. I factor out the a, so that's a times 1 plus tangent squared theta, and that's a nice trigonometric identity that's equal to secant squared theta. So now the denominator just becomes a times secant squared theta, and then all this being with d theta. Okay, so now, of course, we can simplify some things out since we have a division and a division over here. So why don't we actually get to that step? Let me actually now denote this equal sign such that we're actually continuing forward from here. So our bounds are still going to stay the same. So tangent or inverse tangent square root of b to the power a divided by a. Then on the lower bound, inverse tangent of the square root of 1 divided by a. Now we actually if we actually cancel some things out, so tangent square, so that means I'll put a tangent theta on the bottom. I have an ln of b, so secant squared theta, that's also going to cancel. So what this reduces to is just 2 divided by a ln of b, and then this actually follows with a nice trigonometric identity that this simplifies to just multiply with cotangent theta and then t theta. Okay, so simplify things even further, that I can actually factor out this constant of 2 divided by a ln of b. So 2 and then a ln of b, then we have our definite integral, same bounds, inverse tangent of square root of b divided by, or this b to the power a and then divided by a, and then now inverse tangent of the square root of 1 divided by a, and then we're just left with cotangent theta. And this is actually pretty simple to do, since that if you just rewrite cotangent theta as cosine divided by sine, then you just apply that u-substitution for sine, and then this is actually just reduced down, so you get the antiderivative is a natural log function, which says that this is just 2 divided by a times ln of b, and then now our antiderivative is going to be ln of sine theta, and then with our bounds for these two over here. And then pretty straightforward that we just plug in our values back into here. So this is subtraction. So 2a ln of b, and then now I have ln of sine of, so inverse tangent of the square root of b to the power a, and then divided by a, close that off, and then subtract, so ln of sine of the inverse tangent of the square root of 1 divided by a. Okay, so you might be thinking these values, so sine, tangent, inverse tangent, you might think that's where the simplification ends and that's our closed form. Well, not exactly, because we can actually reduce things even further. So what I'm going to do, I'm going to call this variable u, I'll call this variable over here for the value v, and we're actually going to look at things in terms of right triangle. Specifically, we're actually going to apply some Pythagorean theorem for this. So if we look at things, we know that specifically, we know that tangent theta is equal to the opposite divided by the adjacent side. So if I take into this perspective and I were to draw this right triangle, and we're actually looking at this from angle u in this perspective, so that means angle u, and then if you take the inverse tangent of that, so that would have to mean that for this opposite side, this is going to be the square root of b to the power a. And then the adjacent side over here, that's actually just simply just going to be the square root of a. Apply the Pythagorean theorem, so square this plus square that, that's equal to hypotenuse square. What you get that for this hypotenuse is actually just simply just going to be a plus b to the power a. Okay, so now let's do the same thing for the variable v. So if I do this again, so right here, v, apply the same rule, so I have a 1 divided by a, so in other words, this is actually the opposite, it's going to be 1, square root of a is going to be the adjacent, and if you calculate for the hypotenuse, then that means this is actually just going to be a plus 1. And what was the purpose of all that? Well, that actually just simplifies it down, so if you actually replace this back here, so now I take the sine of that variable, and we can actually use this picture over here to actually reduce things even further, such that we have, this is actually going to be 2 divided by a ln of b. So now this is going to be ln, and after taking the sine of the variable over here, so sine and then hypotenuse, this divided by this, so now I have ln of the square root of b to the power a divided by the square root of a plus b to the power a, and then now subtract the ln. So for b over here, that means this is actually just going to be 1 divided by the square root of a plus 1. All right, and now we can actually apply the natural log properties over here to reduce things even further. That this is division, since we have a minus of the difference of the natural logs. So 2 divided by ln of b, and so if we reduce this under a single natural log, so a single natural logarithm, what we have now is that this is going to be the square root of b to the power a, and then now we just multiply things by the square root of a plus 1, and then under that it's divided by a plus b to the power a. Close that off, and we're still not done, because we can yet again still simplify things even further, that if we actually just apply the rules with the square root, that actually goes in front of the natural log. And so what we have is 2 divided by a ln of b, then multiply with a divided by 2, multiplied by ln of b, then add this with 2, so same thing again, a ln of b, then multiply by 1/2, and then ln of a plus 1 divided by a plus b to the power a, and reduce things even further, that this is actually got some terms that cancel, which just leaves with just 1, and then add this with 1 divided by a, and then divided by ln, or 1 divided by a times ln of b, and then multiply by ln of a plus 1, and then divided by a plus b to the power a. And so that is actually our final reduced form for this general closed form of, depending on our values for a to b, so of 1 divided by a plus b to the power x, ranging from 0 to a. So again, I'll reiterate again as the question, what values A and B such that it actually holds the validation for over here such that it converges and it's not divergent, undefined in other words. So leave that in the comments and there you have it. So yeah, that's pretty cool if you ask me.